Hello, everybody. My name is Eyal. I'm here in Florida, and it's sort of early in the morning for me. I hope you've been having a good time until now. Um, I have this presentation, and I'm sharing a screen. I hope you can see it. I think I can hear myself, so let me turn this off. So we're going to talk about genetic algorithms and their applications in machine learning, but also more in general. So I work as a data scientist at Gradle, and if you're a Java developer, you're probably familiar with what Gradle does, and the data science that we do in Gradle has to do with machine learning to decide if we can skip certain tests based on all kind of history and other information, and save some time on when you do merges, or when you just when you have to very often run certain tests, and it will make the process faster. What I'm showing you today is somewhat different. So I've been a Java developer for many years, but now I also develop in Python. I run the Jacksonville Java user group and the Enterprise AI user group, which is a virtual group. And this is the link for that group if anybody wants to join. I also wrote that book about genetic algorithms at some point, and a lot of what I'm talking today is based on that book. And I have this free PDF book on the net, which is meant for Java developers who want to get started with machine learning, and it shows a few places where you can get started, even though you may think that Java is not for machine learning, or you should know Python for that. You can also do that with Java. This is the link for that book. Let's start. So there is something called the infinite monkey theory. Maybe you don't recognize the name, but I'm sure you recognize what's behind it. So I'll give you a second to see that Dilbert strip, which we have probably you've seen before. But the idea is they said that if you have 1,000 monkeys and they just type randomly, there is a certain chance that eventually one of them will come, or something will come out which is equal to what Shakespeare wrote. However, obviously it can take an infinite amount of time. The question is if we can maybe direct that randomness and not make it exactly completely random, if we can actually get the results we want faster. So here is something that's sort of equivalent, maybe, in a way. Can we have monkeys create the Mona Lisa rather than Shakespeare? So if we have that image of Mona Lisa and we have those triangle monkeys, and what they do, instead of typing in a typewriter, they put those random triangles in the picture, and the triangles are of a certain, each triangle has the location and the three vertices, and it has a certain color, and it has a certain transparency. And let's say you start with a black background, and then you start putting triangles on it. And let's say that we let every monkey put randomly 100 triangles like that on a picture. Can we actually recreate the Mona Lisa this way, or something that sort of resembles the Mona Lisa as much as it can with having just triangles and straight lines? So I'll show an experiment that I ran, and so that the search is starting with random, but then the idea is that we take the random solutions that are sort of have something promising about them, we try to combine them together, and again we get a new group of less random solution. We try to combine them together again, the better ones, and we go through a process that is a genetic or evolutionary process. And what you see here, we have generations, so you can see some landmarks, which are the number of generations you can see here. So there are 100 triangles, and you can see that after 100 generations, we start to see something, and then it sort of gets similar and more similar. And if we continue to thousands of generations, you can see that at the end, like after 5,000 generations, it's really getting there. And you can squint your eyes sort of, because when you squint your eyes, you sort of do a low pass filter. You sort of turn the straight lines to more soft. And when you squint your eyes, it's quite similar. So what did we do exactly to do that? Let's just show first that we can do, we can use the same technique that I'm going to talk about that we use here. We can use for all kind of other problems. So here is a problem. Let's say you want to pack your bag, go to a conference or something, and so maybe it's more like this stuff you need to pack in the bag, and but the bag is limited, so you have to decide what you want to pack, what will give you the most bang for your space or for the weight limit. So you can't fit everything in the bag. Each item has a certain value to you and has a certain weight, let's say, and the total weight is limited. So what is the combination of items that will give you the most value? And that is called the knapsack 0-1 problem, because you have a list of items and each one you can either take it or not take it. There could be variations where you can take maybe several of the same items, etc. So this is a combinatorial problem because you have to decide what is the combination of perhaps ones and zeros, ones you take and the ones that you don't take, and try to maximize the value. So those algorithms can sell the same algorithm, very similar algorithm to what I show with the Mona Lisa, can solve this problem. Also, this is another combinatorial problem that's known as the traveling salesperson problem. You have to basically go through all those cities. They have distances from each other. You want to go through all of them just once, come back to the same place you started, and you want to minimize the total distance. So this is a combinatorial search where the order of the cities is what you have so many different ways that you can order those cities. Actually, here I think there are 29 cities perhaps, and you have a huge amount of combinations that you can try. So you need something that's not completely random, that is better than random to figure it out. The same technique again can work here, and this is like the best solution for this problem. This is the path. Of course, there are other ways to solve those problems, but I'm just showing you that all these problems can be solved by the same technique that I call genetic algorithms, which I still didn't explain too much about, but I'm showing you that it is very versatile. Here's another problem. This is called a constraint satisfaction problem, because here we have the queens. We have to put them on the chessboard, but they have all kind of constraints. They cannot be on the same row or the same column or the same diagonal, because then they sort of threaten each other. So you want to put, if there is a 16 here, it's an imaginary 16 by 16 chessboard, which is more complicated than the 8 by 8, which is the original problem. But there are so again there are many combinations. There are also quite a few solutions, but you can look for a solution, and here you also have the constraint. It's not enough to just be able to place those on the board, but there are a lot of combinations that are not allowed. And lastly, there is a regular sort of what we maybe learned in calculus or even high school, where we have a function that is a floating point function, and we want to find the minimum points or sometimes the maximum points, because this function represents maybe cost or anything that you want to minimize, or it can the other way around. It can maybe represent accuracy, and you want to maximize it. This particular case also shows that there are four minima, and they're all equally good. So sometimes it's enough to find one. Sometimes you actually want to find all of them. My point is that all these different kinds of problems can be solved by a genetic algorithm, which is what I'm going to talk about. Because so what we really have is different problems, but almost always the same kind of solution. The solution is very similar. So it is sort of it's a powerful proposition here to have something that can solve many kinds of problems. So I'm going to talk a little bit about that, how it works. So genetic algorithms is a family. There are all kind of variations to it. And they were inspired by the principles of Darwinian evolution. So we will talk what that means later, but the idea is we take this process, a very simplified version of what Darwin prescribed, and we imitate it in using software, and we create this process. And it can usually, in many cases, practically, it can produce high quality solutions for problems of the kinds that we saw. And learning is one of them, because learning is really usually a kind of search and optimization. In learning, we usually try to optimize, like minimize the error, maximize accuracy. We have constraints, etc. So learning, optimization, search are very similar problems. And it has some interesting qualities, this kind of search, that can overcome some of the issues that other traditional algorithms encounter often. Let's talk about Darwinian evolution. So there are several principles. One of them says that you have a population of individuals, let's say people or dogs or any kind of population. They're not the same. Each one, even though they're the same species, each one of them has different properties and traits. And when we or they reproduce, they pass some of these traits or properties to the next generation, to the offspring. And the ones that, generally speaking, in evolution, the ones that have the traits that are better adapted to their environment, which we can call it the problem that they're trying to solve. They're trying to basically optimize, so they will find the most food, for example, or be able to hide from their predators or catch their prey. So the ones who have the better traits that enable them to do that, usually they have a better chance of surviving, and by surviving, they have a better chance of reproducing and basically pass those successful traits to the next generation. Or they will have more chances of having offspring. It is always possible also for a weak individual to succeed to have offspring, but it's just that statistically, the more successful ones will have more representation in the next generation. So we're trying to do something similar here. If we have a problem, we start with a bunch of random solutions, like we saw those random triangles. We had 100 random triangles, but a lot of them. Each individual had 100 random triangles, but then we enter the main loop that basically runs some kind of evolution on this population and creates generations and generation, and we will go into it in the next slide. And at the end, we say, okay, we evolved long enough. We had like 5,000 generations in the case of Mona Lisa. That's maybe enough. We can stop here. Or we can say, okay, that we could not find it. That's the best we could do, or maybe it wasn't good enough. Let's try something else. So how does this evolution works in the main loop? So when we have a generation of a solution, let's think of those triangles. We now take each picture that has 100 triangles, and we need a way to evaluate each and say, okay, how similar is this to the Mona Lisa in this case? Or if it was, let's say, some kind of a model, we can say what is the accuracy of the model, or what is the recall, or the error, or the loss, or whatever it is that we want to compare. And we we sort of see that each individual, like we said in evolution, can have a different amount of success that we call fitness. So some of them are better fit, some of them are less, and then we do a process where we try to select the better ones, but it is statistical. You have a chance to also select ones that are not, but the ones that are more successful will have better chances of being selected, and we select them to do a crossover, which is a process of mating. So we basically select the parents of the next generation. If we do it correctly, then the parents of the next generation are generally the better parents in the population, and then we mate them together, and hopefully the better traits from each parent find good traits from the other parent, and they become some of them at least become better than both their parents. And then we have in general in average, we have a better generation than the previous generation, because it takes the good parts perhaps, or some of them get the good parts from both parents. We can also introduce mutations, just like in the evolution that we're familiar with, and we can just randomly change things just to introduce more new blood, if you want to call it, or some new possibilities that did not exist in the original population. When we go through this, you create a new generation, and then we just repeat. We evaluate all the ones in the generation. Usually the generation will be better than the previous if we know what we're doing. And then we just repeat, repeat, repeat. And at the end, we can just say, do I have it here? Okay. At some point, we decide to stop. We said, okay, let's say we can decide ahead of time. We will go either to 1,000 generations or until the results we get is so and so. It's the error is smaller than a certain value, etc. And then we stop. And then we still have a population of solutions, and we at that point that we take the best of the solutions, or sometimes maybe we need more than one solution, and we can take the 10 best or whatever we want. And to be able to do that, because if I go back here, if you want to do like a crossover, to take two solutions and make an offspring, or to take a solution and do mutations on it, you need to somehow represent the solution in a way that allows you to do that. And we call it a chromosome, sort of like in genetics, but sort of more simplified, way simplified actually. So here is a very simple chromosome. Like when we were talking about if you wanted to select items to pack in the bag, then we could have just said that each solution would be just a string of one of zeros. Each one of them represents a certain item, and we either take it, it's one, or not take it as zero. And so this is a simple, very simple chromosome. It works for a lot of problems. But different kind of problems will have different kind of chromosome. If we had that floating point function that we wanted to optimize, there would actually be floating point numbers, which is one way to represent it. Or you can sometimes represent each floating point number with a lot of binary bits, but that was an older way of doing it. Nowadays we'll just use floating point numbers, and we'll have a way to combine them together and do things with them. If it was the city where we have to travel through a sequence of cities, these will be the numbers of the cities, like 1, 2, 3, 4, 5, 29, etc. But the idea is we have a chromosome that usually looks like a string, like a list maybe, or an array. And so here is like I guess I went ahead of myself. This would be like if we have 5 cities and we have to order them in a certain order, or some 5 items, that would be a chromosome for that. That would be a chromosome for a floating point. And now that we have to be able to take that chromosome and evaluate it. So in the case of the packing a bag with items, we will take this chromosome and we'll say, okay, so the items we're packing is this and this and this and this and this. Let's see that the total weight of them is not too much, which is sort of a constraint here. And let's see what is the value of all these items, because we want to maximize the value. So the fitness function will give us the value, and we want to maximize it. So the fitness function, we have to have a way to take this evaluation, this representation of a chromosome, and convert it and evaluate it. Sort of what I said. Okay. So what comes out is the fitness value, and then we use the fitness value to compare them to each other, and now we have to select the better individual. So there are all kinds of ways of doing that. So it's sort of random, but it's based on probability, and the idea is that the chances of selecting an individual that has a better fitness are greater. So it will contribute more to the next population, because the ones that we select become the parents to the next generation. So originally there was something called roulette wheel selection. So if we had several individuals, here 6, we would sort of make this roulette wheel and give each one of them a slice that is sort of is proportional to how good the fitness, how high the fitness of this individual is. So for example, E has the biggest fitness, and we calculate here that it's 40% relatively to the other ones. So E has this huge, almost half of the roulette wheel, etc., while this yellow one is D. It has only 3% chances of being selected. So we roll this roulette now, and every time we stop, and whatever this is pointing at will be selected. So there is a chance that this one will be selected, but there's a much bigger chance that this will be selected, or this will be selected every time we do the selection. This has some issues with it. I won't go too much into it, but there is a much easier to implement way to do it, and it's called a tournament. And what we do here, we just decide what is the tournament size. Let's say here it's 3. We randomly pick 3 individuals, and then we take the best of them. So obviously, when we do this, if the size is 3, the two, like the A and D here that have the least amount of fitness, they will never get chosen because there will always be the third one will be better than them. So the bigger the tournament size, the more we push towards the higher, the better solutions, and we neglect the lower solutions. So tournament size of 2 actually is very common. We just take 2, and the better one continues, becomes a parent. And we just keep repeating it until we have enough parents to make the next generation. And now the crossover is where we take the two parents and we recombine them, sort of. So we take building blocks from both parents. So this, what really the chromosome, we call it a sort of collection of building blocks. In the case of the binaries, it's the easiest to to imagine it or to show it. So if we have two parents that are binary chromosomes, we just have a cut point, we cut it, and we just swap those pieces between them. We don't show it here. If we have other kinds of chromosomes, like ones where the order is important or its floating point, then this operation is more complicated. I won't go into it, but there are already algorithms to do that, to basically take two and somehow mix them together and come up with two new ones that are valid. And mutation, again, in the binary case, is very easy. We can just pick certain bits in the chromosome and flip them. And again, you can do that. There are ways to do it with floating point numbers as well, or where you have a certain order, then you can, for example, just take two and switch them around. There are many ways of doing that. And it's all basically well-established methods. So when we run genetic algorithms, there are some differences from traditional algorithms, which are pretty obvious. We have a population of solution, not just one solution that we modify. We have a genetic representation that we call the chromosome, or you can call it other names as well. And the behavior in general is probabilistic. And advantages of that is that it's usually it's generally considered a global optimization. It means that it is relatively immune to local maxima or minima issues. Like here, you might remember this from calculus, or you might have seen it elsewhere. But for example, here you have a maximum that is local. So some search algorithms will find it and they will be very happy with it because they think it's the best for its environment. The same thing here. This is looking for the minimum. They might find this and get stuck here, and they will miss those two that are actually. Why genetic algorithms are relatively immune to that? Because they search with a large population and they jump around a lot. They don't get stuck in one local place. They jump around because you can take solution from here, the solution from here, etc., and put them together, and you find yourself in a different place. And because of the mutations, and because you just have you have a better coverage because you have a population. Sometimes you don't have a good representation of the problem, like in the case of maybe Mona Lisa. You can't really write a function that you want to optimize, and you can't write a derivative to it. You can't really make any calculations on an analysis of the function. You just know that this comes in, this comes out, and is it better or not. You just, when it comes to genetic algorithm, it's enough to just being able to map the chromosome that you have to the individual, which let's think of it. The chromosome can be the locations of the triangles and the colors of the triangles, all the information around the triangles, and then you get an image somehow, and then you just have to compare this image to the Mona Lisa. So you just have a way. You need a way to evaluate, or sometimes just enough to compare the individuals, even if you can't directly evaluate anything. As long as you can have two of them, you can, for example, ask a person, do you like this better or do I like that better? And you don't know what they're thinking, but you know the result. They like that better. So another thing is that genetic algorithms, they work on a population, which also we will see it in the disadvantages. It makes them slower, but at the same time, they lend themselves to concurrency because we can do a lot of things at the same time. We can evaluate all the individuals at the same time. They're not dependent of each other. It's sort of embarrassingly parallelizable. We can also, when we do the crossover, we can pick pairs and cross over them, and it's independent of doing it with other pairs. So this can make up for the fact that you have generations and population. And it's generally resilient to noise because you keep doing things over and over and over. You try different pieces. So noise means that sometimes you will try to evaluate the same solution twice, and you will get maybe somewhat of a different solution, different evaluation. And sometimes it will perform better than another time. But this is very repetitious process, and it's generally canceling this kind of noise. Another thing that is interesting in genetic algorithms, you can find a solution that you like, but sometimes over time, the problem changes a little bit. If you keep doing this process in the background, if the change is relatively slow, it will catch up with it. So you don't have to go and solve a new problem. You can always continuously run this. And sometimes you can also find better solutions for without changing the problem. Perhaps you will encounter a better solution that you haven't seen before. But also if the problem changes to some degree, just like evolution of a species, if there is a certain change that needs them to adapt to new conditions, that will keep doing that and could adapt to to the new conditions or to the new problem. The problem is, or the disadvantage is, it's not necessarily a big problem because it was done for so many problems that it's relatively does not require rocket science, but you do need to figure out what will be the chromosome and what will be the operators that you will run on this to represent your problem. And like I said, there are many already existing algorithms and patterns to do that for a lot of kinds of problems. And computationally intensive, that is the case. We can, like I said, can make it a concurrent and help, but it does need a lot of calculations when you have a population of solutions and you have many generations. While computational over time has actually become less of a problem since I started working on genetic algorithms many years ago. So there is a certain a trade-off here. You can decide maybe one of the, I don't know if it's the next point, but yeah, let's stay here. So one of the things when you do when you try to define, you have to evaluate the problem and say, okay, what will be the size of the population? What will be the number of generations that I'm going to say to run this algorithm for? And over time, you just get better at evaluating it because you don't want to throw a lot of, you don't want the population size to be too big and the number of generations to be too long, etc. So you need to sort of optimize your search so you won't waste your resources. So to match the problem with what you throw at the problem. And also, because it's sort of a heuristic, is not guaranteed to find the best solution. But practically, it's known to find good solutions in a reasonable amount of time. So a lot of algorithms will find the best solution with an infinite amount of time, which is not very practical. Okay, a few words about the deep framework. If you use Python, you can use genetic algorithms in pretty much any language. There are frameworks. You can write it from scratch if you want. It's possible, definitely possible, but there are frameworks that already have a lot of the work done in them, so it's usually a better idea. In Python, also, there are many Python frameworks. The one I've been using is called the DEEP, Distributed Evolutionary Algorithms in Python, and it's pretty comprehensive, and it has a lot of features to it and a lot of interesting, let's say, built-in ways to solve different problems that can save you time. And it comes from this university. And they have they have a toolbox and all kind of data structures and some ways also to enable concurrency if you're into that. You can use it with this license. And it also, like I said, genetic algorithm is sort of a part of a bigger family that's called evolutionary computation. So there are some other relatives of genetic algorithms that are also used sometimes to solve problems. They are less common, but they exist, and this framework supports them as well. And here are a few other Python frameworks that you can look into if you don't like the deep, or if you just want to try something else. Okay, so let's go to machine learning. I'm skipping a few slides here because I presume that people here know already about what machine learning is and what model is, but basically, so what I'm going to show you now, sort of quickly, is how genetic algorithms can be used in machine learning, and they can be used in many ways. This is a problem. I'll go very quickly over it, but here you have 7 kind of animals. You have 16 features that come in, and it's a known data set called the zoo. You need to classify the animal, if it's a mammal, bird, etc., based on the 16 features. But we have feature selection, which is something that we do, or sometimes we don't. We sometimes tend to think that the more information, the better. But actually, sometimes it's better to drop some of the features because they introduce noise or they're redundant, and they actually decrease the accuracy of the model. So if we take this problem and we want to select a subset of the features and see if a subset of the feature is better, then I experimented with that, and generally it's better to have less features because it will be training time is shorter, the accuracy can be better. You can always it will always generalize better when the complexity is smaller. So also the models are easier to interpret and basically they take less memory, etc. So I'm going quickly through it, but there is a data set that you can find easily. It's called the zoo data set, and here is a model. We put all these features on one side, and then on the other side, it's a classifier. This is classification of 1 out of 7 species, or I'm not sure what to call those, types of animals, let's call them, those classes of animals. So, which we apply the genetic algorithm to try to find the best subset of features that go in, and we just use a binary chromosome of length 16, and basically 1 or 0 says, are we going to use this or not going to use this? And if we don't use it, we just drop that column from the data set, and we use the tournament selection in this experiment. 2-point crossover means we will cut it in 2 different points, and we will take the pieces and change it with the other parent. And we flip bit mutation, which is what we saw before. And the way you evaluate the function, the fitness is, like I said, you remove the data column that have a 0. So basically now you only have the features that you select, that have the 1, and then you can, in this case, I did a k-fold cross-validation. It's a relatively small data set, so you can actually do that very quickly. And then you take the mean accuracy over the k-folds. You find what was the accuracy for those selected features. And then also, if we have two solutions that one of them has less features, so we want to select the one that has less features. So we give a small penalty, which can be used as a tiebreaker. If you have more features, you pay certain penalties, so it will sort of decrease your accuracy in a way, or you will have one measure that you measure the accuracy, one that you measure the number of features, and it will be a combination of the two that will give you the fitness. So what you see here in this experiment, it shows you what the best solution. So you see that the top 5 solutions use either 6 or 7 features out of the 16, and the one with the 6, they all get accuracy of 0.97, which is higher, quite a bit higher than the original accuracy with the 16 features. But also you see that the fitness of the one with the 6 is a little better than the one with the 7 because they paid a small penalty for having 1 extra feature. So the 97, because it had 6 features, it was decreased by 0.006. These were decreased by 0.007 in this case. So they're a little less. So the idea was that the number of features will not be more important than the accuracy, but given the same accuracy, then the less features will win. So, and actually, if you go further into it, you can find, I think, a better solution with 5 features. So the results here quickly just shows us that actually we got better accuracy with less features. And these are the 6 features that are enough that were the best. The features that provide 97%. Okay, so I don't have a lot of time left, so I'm going to go a little faster. Another thing that is done often with models is hyperparameter tuning. The idea is these are parameters of the learning process of the model, and we set them, and then the model is learning. And when we set them differently, the model is learning again, and we try to find the best hyperparameters like the learning rate, momentum, etc., depending on the model. And we can do a grid search where we create a grid like this, and we search over all the possibilities in the grid. Like here we have three different hyperparameters. One of them actually is integer, one of them is continuous, and one of them is like enumerated. And we can create a grid like that and go search throughout the entire grid, or we can do random on that grid. So what we can do is you can use a genetic algorithm. We can use it on the grid. Okay, I'm not going to go into the implementation here, but let's just say that there are two ways to do it with genetic algorithm. You can either use the grid, but only use certain locations on the grid, and the combinations of the grid is what you're going to use for your chromosome, or you can just search it over the entire space that you define the boundaries. Like you can go back to those boundaries here, and you can basically search on the space. Because another thing genetic algorithm can do that I didn't mention too much, but you could have a mixed parameter search. You can search on integers and float numbers and enumerated at the same time if you want. And you can just search over the entire space that is, let's say, you can say anywhere between 10 to 100, etc., and so forth. So you don't have to limit yourself to just that grid. This leads us to other things that you can do along the same lines. So you can use genetic algorithms for feature engineering, for architecture of models, like especially deep learning, where you can have different number of layers and different ways to define the shape of the network and the different components of the network. You can use it to select model when you have different kinds of model and you want to know what model perform the best, or what models with what parameters perform the best. You can use them to create an ensemble from different models and find the best combination of models to put together. And you can use them more generally to create an entire pipeline to decide basically what you do with the data, what you do in the feature engineering, what features to drop, etc., and then what model you will do, and post-processing, etc. And all this eventually led to what we call AutoML. So there are many frameworks also that do the AutoML automatically. That's built in, or there are frameworks that are dedicated to AutoML. A lot of them use genetic algorithms, at least for part of the process, and there is one called the TPOT, that is pretty much using the genetic algorithms for the entire pipeline. And this is a Python framework that you're welcome to check out. That's the acronym, Treebase Pipeline Optimization Tool. One more thing that I wanted to talk about, and I have a few minutes left, is reinforcement learning. Reinforcement learning, I'll just mention a few words. It's an interaction between an agent and environment. The idea is that unlike supervised learning, where you immediately get a feedback, you have an input, you give it an input, there's an output, and we immediately tell the model this was off, or this was good, or this was that good. Here, the agent does all kinds of interactions and sometimes has the feedback only at certain points in time or after a whole thing has happened. But generally, we're talking about moving to a new state, getting rewards, but we can look at it as interaction with the environment, and then sometimes you get some kind of feedback, which is a reward. So a genetic algorithm can be used to construct agents that try to maximize the reward that they get from the environment, and basically do what they do and eventually get the feedback, and then use that feedback to construct a new generation of agents. So you will have, when you do it with genetic algorithms, you will have a population of agents. Each agent will be an individual, and you will try to find an agent that does exactly what you want. And it can be used for a lot of problems. I'm going to show, I don't know if, I have an animation, but I don't know if I can show it now. So Basically, this is called a card pole, sometimes called an inverted pendulum. Imagine that you try to balance this stick on your hand by moving your hand left and right. So this card pole, this black rectangle here, can move right or left, and it tries to balance that pole that is attached to that point, and it can like fall right or fall left, and you want to create something, some program that gets the input. The input will be some status of that pole, and the output will be basically go right or go left. So the OpenAI gym is a collection of problems of this sort, and some of them are simple, some of them are a lot more complicated. But this is sort of a very small problem here, but it's a good example or a benchmark. And the way they defined it is the inputs are the position of the cart, the velocity of the cart. The cart is that black rectangle, the angle of the pole, and the velocity at the tip. So it will tell you it's running, it's falling to the left, falling to the. So these are the four inputs that you have when you interact with the world. The agent gets those inputs, and the agent needs to decide if to push to the left or push to the right. That's it. So the way that I solved that with the genetic algorithms, I created a controller that is made of a neural network. And the neural network will have obviously four inputs, which are the inputs to the problem. We'll have an action output, which will be 1 or 0. And I decided to have a hidden layer of 4, but it could have been anything that I could basically you can experiment here. Here, because it's not a big problem, you just need one layer and only a few. So that worked out okay. And what was looking to find those weights, as you probably know, the neural network here, I'm not calling it deep learning network because it's not very deep. It is just one hidden layer. But this neural network has weights. Each of these nodes and this node, not the input nodes are just there to distribute the input. But the hidden layer, each of them has 4 weights and 1 bias, and this also happened to have 4 weights and 1 bias. So you have 25 parameters here that the genetic algorithm is actually looking for, which are the weights and the biases. And the way and what it does, it proposes those weights and biases, an individual, and then it just simulates to calculate the fitness of this individual. We run this simulation. It doesn't necessarily animate it. It runs it in the background, and it finds how long it takes to the carpal, how long the carpal can balance it up to a certain point. And then it says, okay, this individual was better because it was able to balance that pole for longer than others. And this is how the next individuals get selected. And at the end, it came to the point, it's very quickly, it can find the individual that those weights and biases for the network that will control the cart, and it can just control it and basically go forever, and it will never fall. Then you can try more complex problems, but the idea is the same. Now, just one last thing before I end here. So what you see here, I had to decide in advance that this will be the individual will have 4 hidden layers, etc. And I'm looking for 25 parameters, and I ran the genetic algorithms for that. Obviously, I could have said, okay, I don't know how many nodes I want, or how many layers I want, or what exactly this will look like. And I could have maybe created a genetic algorithm that will look for all these things together, sort of like in the way of the AutoML. It will look for several things at the same time, the structure and the weights. So that can be done, but actually there is a framework that's called NEAT, which is what sort of illustrated this. I'm not going to go into it, but that was actually created about 20 years ago. And the idea of that is it's an algorithm that dynamically, it starts with a very simple net. It will actually starts just with, you don't even see it here, but it will start just with the input and output. So in our case, it would have started just with 4 and 1 with no hidden layer. And as it evolves, it tries to add nodes in the middle. And it also does different things, so not to add too many, basically. There are some certain things done in this algorithm. It's sort of interesting. Also, it tries to divide the population to different groups, so it will not it will sort of compare oranges to oranges, but it will try to prefer the simpler solutions that solve the problem. This is just an interesting illustration that somebody came up with. The idea is that over time you can evolve the network to be more and more complex. And you see, it does not necessarily have to have a full dense network. It can have nodes that are basically, it can have a partial layer. It can have nodes in between those, but none in between those, etc. So I hope all this sort of gave you a taste for genetic algorithms and what you can do with them, and perhaps you will try some of material available. There are a lot of frameworks, there are a lot of sample software and examples of all kinds of problems being solved. So I encourage you to go out there and look for more and see if you can and how you can combine it in your machine learning experiments and other experiments. I've had quite a few people telling me that they use it at work in different ways, not necessarily in machine learning, but also in machine learning. So thank you very much. That was my pleasure. I don't know if we have, I think I'm just past my time. So I'm not sure how it goes with questions and answers, but you can contact me. My name is very unique. You can find me easily and you can ask me questions and I will be happy to answer.